Hello students, now I am going to discuss about the blocks of elements. As you know, there are four types of subshells: S subshell, P subshell, D subshell and F subshell, and therefore there are four blocks of elements: S block elements, P block elements, D block elements and F block elements, right? So S block elements, which are S block elements? The elements in which the last electron enters into s orbital are called S block elements, right? And as you know, in S subshell there can be only two electrons, either 1 and 2, and hence the general outermost electronic configuration of S block elements will be NS1 and NS2, where N is the outermost shell, right? And remember one thing, in case of S block elements, the number of valence electrons is equal to group number of that element, okay? As for example, if I have to write the electronic configuration of potassium, so you know atomic number of potassium is 19. That means its one atom has 19 electrons. Therefore, its ground state electronic configuration will be 1s2, 2s2, 2p6, 3s2, 3p6 and after this 4s1. So look here, in potassium, the last electron enters into s orbital and therefore potassium is S block element. And since it is S block element, therefore its group number will be equal to its number of valence electron. Here the outermost shell is 4 and in its outermost shell there is only one electron, therefore its valence electron is 1 and therefore its group number is 1. The group number of potassium is 1. Since here the outermost shell is 4, therefore its period is 4. It is in the fourth period of group 1. And since last electron is in s orbital, therefore it is a S block element, okay? As for example, if I have to write the ground state electronic configuration of barium, atomic number of barium is 56 and therefore write its noble gas configuration or condensed electronic configuration. As you know, before 56, which noble gas comes? So before this, the noble gas which will come is xenon, atomic number of which is 54. Therefore, for 54 electron we can write here xenon. Now xenon is the last element of Fifth period, helium, neon, argon, krypton, xenon. Xenon is the last element of fifth period. That means barium must be in the sixth period, and therefore here the outermost shell will be 6, in which maximum 6s and 6p subshells may get electron. Now, since outermost shell is 6, therefore the penultimate shell will be 5, in which D subshell may get electron, and antepenultimate shell here will be 4, in which F subshell may get electron. Now, fill up these subshells with electrons according to above rule. Among these 4 subshells, the least value of n plus L is for 6s, and therefore among these 4 subshells the lowest energy is of 6s, and therefore first of all 6s will be filled up with electrons, and as you know s subshell can have maximum 2 electrons, so we can write here 6s2. 54 for xenon and 2 here in S, 56. So we have to complete 56 electron, and we completed. So here 4f, 5d and 6p subshells are not getting any electrons, therefore there is no need to write these subshells here. Therefore we can write it as barium 56, xenon 54, 6s2, right? We will write those subshells only which are having electrons, right? Now here look, in barium last electron is in s orbital, and so barium is s block element. Here the valence electron is 2, therefore its group number is 2, and here the outermost shell is 6, therefore it is in the 6th period. So we can say barium is in 6th period of group 2. Okay, now after S block element we will discuss P block elements. P block elements. What are P block elements? Those elements in which last electron enters into p orbital are called p block elements. Okay, and as I have discussed earlier, in case of the outermost shell, if suppose outermost shell is N, so then in outermost shell there can be only S and P subshells of the outermost shell which may get electrons, right? Among NS and NP, NP subshell has higher energy, and so first NS will fill up with 2 electrons, and after that electron will enter into p orbital of the outermost shell. And as you know, in p there can be 1, 2, 3, 4, 5 and 6 electrons. So NH2 NP1 2, NH2 NP6. Okay, now the p block elements will have the general outermost electronic configuration like NH2 NP1, NH2 NP2, NH2 NP3, NH2 NP4, NH2 NP5 and NH2 NP6. Right? Here the last electron is enter into p orbital, so they will be the p block element. And remember one thing here, what? In case of p block elements, group number is equal to number of valence electrons plus 10. In case of p block elements, group number equal to number of valence electrons plus 10. Okay, now take an example. Suppose we have to write the ground state electronic configuration of thallium, and as you know, atomic number of thallium is 81. Okay, now write its ground state noble gas configuration or condensed electronic configuration. So before 81, which noble gas comes? Xenon. Up to 54, xenon, we will write xenon. Now xenon is the last element of 5th period. That means thallium is in the 6th period, and since thallium is in the 6th period, therefore here the outermost shell will be 6, in which maximum 6s and 6p subshells may get electrons. Now outermost shell is 6, so the penultimate shell will be 5, in which D subshell may get electrons, and antepenultimate shell will be 4, in which F subshell may get electron. Before 4th shell there will be the 3rd shell, and after F G subshell comes, but as you know 3G is not possible. The first G is 5G, so we will have to stop here for F up to 4F. Now we have to fill up these subshells with electrons according to Aufbau rule. Among these 4 subshells, the lowest energy is of 6s, so fill 6s with 2 electrons first. Now 4f, 5d and 6p subshells have the same value of n plus L, and as I had discussed earlier, in case of multi-electron species, if the subshells have the same value of n plus L, then that subshell will have lower energy which has lower value of n. So among 4f, 5d and 6p, 4f has the lowest energy and therefore it should be filled up with 14 electrons. After that 5d will get 10 electrons. Now we have to complete 81 electrons. 54, 14, 68, 10, 78, 280. Now 1 electron is remaining, and that remaining 1 electron will enter into 6p. So you can see here in thallium, the last electron is entering into 6p p orbital. So thallium is in p block element. Thallium is a p block element. Now look here. Its outermost shell is 6, and in its 6th shell, that is in its outermost shell, total 2 and 1, 3 electrons are there. Therefore its number of valence electron is 3, but since it is a p block element, therefore its group number will be valence electron 3 plus 10, so group 13. Now since here the outermost shell is 6, so this will be in the 6th period. So you can say thallium is in group 13 and in 6th period, right? Now we will discuss about D block elements. D block elements, right? As the name suggests, in D block elements, the last electron enters into d orbital of the penultimate shell, because as you know, in the outermost shell there can be only s and p subshell of the outermost shell which can get electron, and d subshell gets electron in the antepenultimate shell. Therefore we can define here those elements in which the last electron enters into d orbital of the penultimate shell are called D block elements, right? Now the general outermost electronic configuration of the D block elements can be written as if I suppose N is the outermost shell, so here the outermost shell S can have either 1 or 2 electrons. But there is one element named palladium which has no S electron in outermost shell. Okay, now since if outermost shell is N, so the penultimate shell will be N minus 1, in which D subshell may get electron and D can have electron 1 to 10. Therefore, the general electronic configuration of the outermost shell in case of D block elements will be N minus 1 D 1 to 10, NS 1 or 2, right? But in case of palladium, NS has 0 electron, but still it is a D block element. In palladium there is D10, and we will discuss the electronic configuration of palladium later on. Right now, remember one thing: in case of D block elements, S electron of the outermost shell and D electrons of the penultimate shell both involve in bond formation, both involve in number of valence electron. Therefore, in case of D block elements, valence electron will be equal to sum of electrons of S of the outermost shell and D electrons of the penultimate shell, and therefore in case of D block elements, group number will be equal to S electron plus D electron of the penultimate shell. Okay, therefore you can write, in case of D block elements, group number is equal to S electrons of the outermost shell plus D electrons of the penultimate shell. Right now, take an example. Suppose I have to write the ground state electronic configuration of mercury. As you know, atomic number of mercury is 80. Right now, write its ground state noble gas configuration or condensed electronic configuration. As you know, before 80, which noble gas will come? Xenon, and its atomic number is 54. Now, xenon is the last element of 5th period. Therefore, mercury will be in the 6th period. So here the outermost shell will be 6, in which maximum 6s and 6p subshells may get electrons. Penultimate shell will be 5, in which D subshell may get electrons, and antepenultimate shell will be 4, in which F subshell may get electron. Now fill up these subshells with electrons according to Aufbau rule. Among these 4 subshells, the lowest energy is of 6s. Therefore, we will fill 6s with 2 electrons first. After that, 4f will get 14 electrons and 5d will get after that 10 electrons. Here 54 and 14, 68 and 10, 78 and 2, 80. 80 electrons completed. Therefore, 6p subshell is not getting any electron here. Therefore, there is no need of writing 6p here. So, this is the ground state electronic configuration of mercury. Now look, among these 3 subshells, 4f, 5d and 6s, the highest energy is of 5d, and as you know, the last electron remains in that subshell which has the highest energy. So here the last electron is in 5d, that is in d orbital. So mercury is a d block element. Now, since it is a d block element, therefore how can I find its group number? As I said earlier, in case of d block elements, group number is equal to s electron plus d electrons of the penultimate shell, 10 plus 2, that is group number 12. It's group number 12. And since here the outermost shell is 6, so it is in the 6th period, right? Now we will discuss F block elements. Look here. F block elements are also called inner transition elements. F block elements are also called inner transition elements, right? Now look here. Cerium atomic number 58 to lutetium atomic number 71. From cerium 58 to lutetium atomic number 71. These 14 elements are called lanthanoids. These 14 elements are called lanthanoids. These 14 electrons from cerium, that is atomic number 58, to lutetium atomic number 71 are called lanthanoids. And thorium atomic number 90 to lawrencium atomic number 103. From 90 to 103, these 14 elements are called actinoids. So first of all, remember this, learn this. Elements from atomic number 58 to 71 are lanthanoids, and the elements from atomic number 90 to 103 are actinoids. And all lanthanoids and actinoids are F block elements, and they are in group 3. Clear? To remember this, all lanthanoids and actinoids are F block elements, and they are in group 3, right? So if atomic number of an element is given and we have to find the block and group number of that element, first of all, don't write the ground state electronic configuration of that element. First of all, recall the atomic number from 58 to 71 and 90 to 103. If the atomic number of the given element falls in this category from 58 to 71 or 90 to 103, then they will be either lanthanoids or actinoids, and therefore their block will be F and group number will be 3, irrespective of the electronic configuration of that element, right? But if the atomic number of the given element does not fall in lanthanoid and actinoid category, then first write the ground state electronic configuration of that element and then see the last electron is entering into which orbital, either S, P or D. If entering into S orbital, then S block element. If in P, then P block element, and if in D, then it will be the D block element. Okay? Now, there are 4 blocks of elements: S block elements, P block elements, D block elements, and F block elements. Here we have to remember about F block elements. F block elements have two series, lanthanoids and actinoids, and each series has 14 elements. Lanthanoids are from atomic number 58 cerium to atomic number 71 lutetium, and actinoids are from thorium atomic number 90 to lawrencium atomic number 103. Now, if the atomic number of an element falls in this category, in lanthanoid or in actinoid category, then that element will be F block element and their group number will be 3, no matter whatever its electronic configuration, right? If the given element does not fall in this category, either in lanthanoid or in actinoid, then first write the ground state electronic configuration of that element and then find the block and group number of that element.